Okay, so here we go. Be careful what you wish for. Here are so many exam questions for you to practice, and here I will go through all of them in some detail, talking through the pitfalls as we do. So let's start at the beginning with a nice straightforward SUVAT. So before you do anything, please, 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 can I encourage you to set these up before you get going. You can see from this question that we've got a horizontal initial velocity and we've got a vertical height marked up. So that should tell you that we are going to need both of these. Okay, so set up your two sets of equations, all right, or rather of letters, so that we know what we've got. So vertically we've got a height of 18 meters. Remember, vertically we know that u will be 0. Vertically a is 9.8, and that's all we know vertically. And then horizontally all we know is that we've got, nope, that's not a speed, that is a distance, that's a speed. We've got a displacement of a velocity of 5 meters per second. So first thing we're after 2 seconds to reach the ground. So looking at what we've got, the easiest thing to use here is our vertical. Okay, so in this case all we can use is this one here. All right, s equals ut plus half at squared. Remembering of course that u is 0, so that's going to go. So what we're left with is s equals half at squared. Our s is 18, we've got half, we've got 9.8, and we've got t squared. T squared then comes out at 3.67. T comes out at 1.92, which is approximately 2 seconds. Okay, so there is that one done. Okay. Then on to part 2, we're then looking for the distance from the bottom of the building. So now we're looking for our horizontal distance. So we know that this 1.92 is our time, and remember that time is the one parameter that is the same both in the vertical and the horizontal plane. So now we're using this to try and find ourselves a value for s. So again, we use the same expression, okay, half at squared, except that this time we know that acceleration horizontally is always 0. So this time all of that is going to go. So what we're left with is s equals ut, which is s is 5 times 1.92, and that comes out at about 9.6 meters. Okay, so a nice straightforward SUVAT to get us started. Right, now we've got a vector question, okay? A couple of ways in which you can do this. I'm just going to take you through one of them, all right? I'm going to use a bit of Pythagoras here. There is a relative velocity approach you can take, but actually the Pythagoras one is absolutely fine, okay? So what we've got here is we've got this wind blowing to the west with 50 kilometers an hour, all right? So if we're going to visualize that, I'm not going to actually draw it to scale, but we know that that is 50 kilometers per hour. All right, and we know that relative to the ground, we have got this 200 kilometers per hour velocity of our aircraft. So 200 kilometers per hour, there. Okay, so what we can do here, the easiest way to do this is to then simply say, well, all right, then in this case, what is our resultant? And we know that our resultant is our hypotenuse, okay? So when we do that, we know that we've got 50 squared plus 200 squared gives us our velocity squared. So our velocity squared comes out at 42500, giving us a velocity of 206 kilometers per hour. Now, of course, you could do that by scale drawing should you want to. Okay. What you've then been asked for here is the angle theta west of north, which it must take. Okay, west of north. All right. So think about what we're actually being asked for there. The easiest way to do this, probably with my drawing, but yours might be slightly different, is if here is our north, okay, this thing here, what we're actually looking for in this case is this is our theta. All right, so it's slightly skewed from our one down here, but if you think about the drawing that we've got on this diagram here from the question, here is our 200, here is our 50, so we are looking for this angle here, theta. Okay, so there's a few ways in which you can do that. All right, in this case, what we've got, if I use the example from the exam question, we know that tan is the opposite divided by the adjacent. So we know that tan of theta is 50 divided by 200. Okay, so tan of theta is 0.25, and that makes theta 14 degrees, okay? So your alternative way of doing that would have been, if you'd drawn it out like I have, you could have first found this one, let's call that sigma, all right, and you could have subtracted that from 90 several ways around this one, but the final answers we were after was 206 kilometers an hour at an angle of 14 degrees west of north. Right, nice little multiple choice here. So a velocity time graph with some parameters marked up on it. All you're being asked to do is which of these statements are correct. So let's look at this first of all. Let's look at y. Well, y is simply a rectangle. We know that y is a rectangle of base t and height u. So we know that y equals ut. So immediately that one is correct. Let's look at x. Well, x is a triangle. If we do the formula for the area of a triangle, it's half the base times by the height. Now the height in this case is v minus u. You can see that from our y-axis here, okay? But what is v minus u? Well, think back. Acceleration is rate of change of velocity. So actually, v minus u is equal to at, okay? So if we plug all that back in, what we've got is we've got half t multiplied by at, which is half t at, which is half at squared, okay, and therefore there is our second one that is correct there. Okay, list of units. So this is fairly common to have to turn quantities, units into different combinations of units. So unit for power. Now remember, this is a paper, we have got mechanical power, we've got electrical power, all right, so that's why it features in the chapter 8 stuff. And power is rate at which energy is transferred. So hopefully you remember that power is just joules per second. The second one to think about is acceleration. Well, we know that acceleration ordinarily is meters per second squared, but in order to flip between our units, what we do is think of a formula involving acceleration. Now, technically this may come into chapter 9, but I think we can reassure ourselves that we all remember the formula F equals ma, okay? And in that case, acceleration is therefore force divided by mass. So if we then say, well, all right then, what is the unit for force? Well, the unit for force is the Newton, divided by the unit for mass, which is the kilogram, and there we have it. The unit for acceleration is newtons per kilogram. You may, of course, know that just because you know that acceleration and acceleration due to gravity are the same thing, and you might know that G can be measured in newtons per kilogram because it's the amount of force per kilogram that we apply. So another way around it would be that one. Okay, high performance car has an acceleration of 0.86 g. Calculate the time it takes to reach a velocity of 27 meters per second. 60 miles an hour thrown in there for no reason at all, just to confuse you. Okay, so as usual, look at what we've got. Well, we've got an A, which is 0.86 g. Okay, which if we actually work that out, that comes out at 8.428. All right, and we've got a V of 27. Okay, we assume therefore that it is starting with an initial velocity of 0 and we are after t. So we need something that's got v, u, a and t. So we go for v equals u plus at. All right, and therefore t is just our 27 divided by our acceleration of 8.428, giving us 3.2 seconds. Right, you have to forgive me, this question here doesn't seem to have a number. I missed it out as a different number when I was putting the things together, so my apologies. There is a new question that starts here about the balloon, but apologies for not giving it a number. So you've got 5, then you've got a random question about a balloon, and then you've got 6 reappears later. So the important thing with this one is this is a question where you're going to have to start reading what's going on, okay? The key thing here is that this is a rising balloon, okay? Besides weight, there is upthrust. Upthrust is equal in magnitude to the weight taken up by the balloon. That's going to be key later. And when the balloon is moving, there is also air resistance. So that short passage is key to these parts of the question that come up later on. But to begin with, it says draw 3 arrows labelled W, U and AR to show the directions of the weight, the upthrust and the air resistance. So we know, as always, that weight is going to act downwards. So there is our weight. We know that besides weight, there is upthrust. So upthrust is the force that pushes things upwards. So that is our upthrust. Okay, and then we've got air resistance, which ordinarily we're used to falling objects and therefore air resistance acting upwards. But remember, this is a balloon that is rising. So in this case, what we're going to have is our air resistance is going to be acting downwards, okay? Now you could have a single arrow that was W plus AR, that doesn't matter. Any of those combinations is all right, okay? The length of them at this stage doesn't matter, but what's really important is that you've acknowledged from the question that actually the air resistance is acting downwards and not upwards as we are used to, because we are not looking at a falling object, we are looking at an object that is rising. Right, the balloon is released at time t equals 0. Explain why the air resistance force AR is 0 at time t. Think about what we know, okay? What is air resistance? It's a frictional force caused by air particles colliding with an object that is moving through the air. So why have we got no air resistance at t equals 0? Well, quite simply, balloon isn't moving, okay? So the balloon isn't moving, okay? And therefore, we've got no air resistance. I should just point out as well that you should write things in full sentences when you're actually doing the exam questions. I'm merely trying to speed things up a little bit as I'm scribbling, as I'm going through it, okay? So if the balloon isn't moving, there would be no air resistance. Right, part 2. So this may not look necessarily like it's part of chapter 8, but it is because it's about resultant forces, okay? So we've done resultant forces early on. Use the data to show the resultant force acting on the balloon at t equals 0 is about 0.02, okay? So the key thing here is going back to that information in the question, all right? At t equals 0. Upthrust is equal in magnitude to the weight of the air which would have occupied the volume taken up by the balloon. When the balloon is moving, there is air resistance. Right, at t equals 0, the balloon isn't moving, so we've got no air resistance, okay? So what we've got is we've got a force downwards, all right? And that force downwards is down to the mass of the balloon and the helium, okay? So that force is equal to the mass of those two things multiplied by g, and for that we have a value of 0.343 newtons. And then acting against that upwards, we've got the air taking up the same volume, so the mass of that is 0.0060 times 9.8, which equals 0.0588 newtons, okay? And therefore the resultant is simply this minus this, which gives us 0.0245, which is approximately 0.02 newtons. Okay. Okay, so now we've got air resistance forces increase as balloon accelerates. So we know that from work at GCSE on freefall. A mathematical model to analyse the motion gives the air resistance force is equal to kV, where V is the velocity of the balloon and K is a constant. Suggest and explain, okay? So that means 2 marks, 1 mark for suggesting and 1 mark for explaining a change to the balloon which would make the value of K smaller. So what we're really looking for is something that is going to reduce air resistance, okay? So there are a couple of options you could use here, but they probably all boil down to the same thing. You're looking for anything that suggests streamlining, okay? So any suggestion in terms of changing the dimension or the shape of your balloon to allow it to become more streamlined. So there's your suggestion, and your explanation is going to reduce the air resistance, okay? Because if we reduce the air resistance, then what that's going to mean from our relationship is that for a given value of V, if our air resistance goes down, so is our value of K. So 1 mark for a reasonable suggestion of a way that is going to make the balloon more streamlined, and the 2nd mark for that explanation associated with that, which is that we are trying to reduce the air resistance. then we come back to good old velocity time graphs, okay? Explain why the graph becomes less steep and eventually horizontal as time increases. So again, note that there are 2 marks and it is about explaining. So what you've got to do is you've got to link the steepness of the graph to what is happening and attempt to explain it. So the first thing that we should note here is that our gradient is getting less steep. What does the gradient of a velocity time graph show us? Well, it shows us acceleration. Okay, so you firstly need to identify that the gradient is getting less steep. Okay, and it's getting less steep, and that tells us that there is a reduction in the acceleration. All right, so a reduction in the acceleration. Now think about this. Why would our acceleration be getting less? Well, if you want to change the motion of an object, you have to change the resultant forces acting on it. So if our acceleration is reducing, we must have a smaller resultant force. Why do we have a smaller resultant force? Because the faster our balloon is moving, the greater the value of the air resistance. So the first mark is for identifying that we've got this reduction in gradient, which tells us that acceleration is reducing. But the reason for that is because this is due to a smaller resultant force. All right, so that overall force acting, and the smaller resultant force is because the air resistance has increased as velocity increases. Okay, so there is your reason for that one. Now with this one, we're using this relationship F equals kV. The graph shows that velocity reaches a maximum of 1.5. Show this is consistent with a value of K of 0.016. This is again where you need an earlier part of the question. Earlier on, we worked out the resultant force back up here, okay? This was the resultant force at time t equals 0, okay? Remember, at t equals 0, there was no air resistance. So at that point, 0.02 is the biggest our resultant force is ever going to be, because as soon as the balloon starts to rise, air resistance increases and therefore the resultant force is going to reduce. So the maximum value for resultant force is 0.02 newtons, okay? So if we then plug that in, okay, it wasn't 0.02, I'll plug in my actual value, okay? So the maximum resultant force was equal to 0.025. I'm just going to use my whole value, okay? And if that is equal to the velocity of 1.5 multiplied by k, that gives us a value for k of 0.0167, okay? So that is telling us that the maximum resultant force we're going to get is 0.025, and therefore the biggest value of k we're going to get is 0.016, okay? But the fact is it is a constant, so as that resultant force rises, or rather, reduces, then the velocity is going to rise, but that value of k stays exactly the same. You could do the reverse argument. So what you could do is you could do F is equal to 0.016 multiplied by 1.5, which would then give you a value of F, as long as you then compare it, okay, to the answer from part 2. So going in reverse is absolutely fine, as long as you compare it then with the answer for F that you got in part 2. So question 6, we're on to kite surfing. All right, so again, I'm starting at the beginning because it's worth bearing in mind reading these bits of the questions because they may be useful later on. So you've got a kite surfer on a board being pulled along the surface of the sea by lines attached to the kite, and then you've got a diagram showing the lines and the angle that they make with the horizontal. So you can see immediately this is going to be about resolving forces. All right, total tension in the kite lines is 1,000 newtons, okay? So we know that in here we've got 1,000 newtons. By scale drawing or calculation, show that when the angle of theta is 30 degrees, the horizontal force pulling is about 900. So what we're saying is we're after this force here, this horizontal. All right, so FH, when we know that we've got 1,000 at an angle of 30 degrees. All right, so in doing this, in converting the 1,000 into the horizontal, we are moving through our angle, okay? So that's how it's easiest to think about it. You could, of course, use a bit of trig, but the way to do it here is simply this idea that the horizontal force is the size of the force that we've got multiplied by cos of the angle. So 1,000 multiplied by cos of 30 is 866 newtons, and believe it or not, for our specification, that is close enough to 900 newtons. Okay, now as I say, you could do a scale drawing if you'd rather, but you should still find that you get an answer of about 870, something like that. All right, but don't be put off if you get 870. That's not miles off. It's just that our spec is quite lenient with some of their show that's. Okay, so there is part A. So, explain why the kite surfer needs to have a mass of more than 51 kilograms. Your answer should refer to the components of the force. So if we just go back, we know that there is a horizontal component to our force. So we've just worked that one out, all right, which would be pulling the kite surfer along. But we know also that there will be a vertical component of that force, and that would be pulling the kite surfer up, all right, so potentially off the water. So what we're now looking at is what is the size of that. Okay, so what we're now saying is actually now we need to work out the vertical component. All right, so having had our 1,000 here at an angle of 30, if we resolve that into its vertical, we know that the vertical force will be 1,000 multiplied by the sine of 30 degrees because we are now moving away. All right, if we work that out, that means that the vertical component of that force is 500 newtons. So there's your first mark for identifying that that size of that vertical force is 500 newtons. So the reality is, were the weight of the border less than that, he's going to get lifted off the surface of the water, okay? So explain why he needs to have a mass of more than 51 kilograms. We're basically saying to stay on the ground, okay? Now I'll call it the ground, we know he's on the water. All right, to stay on the ground, weight must be at least 500 newtons, all right, at least. If it's any less than that, he's going to get lifted. So what we now say is that if his weight is 500 newtons, all right, that would be equal to his mass multiplied by gravitational field. So a weight of 500 newtons corresponds to a mass of 51.02 kilograms. Okay, so the important thing here is that if you were to mix up what was weight and what was mass, you wouldn't get any credit. So the second mark comes from equating that 500 Newton force to a corresponding minimum mass of 51 kilograms, okay? You could, of course, do the reverse argument. So you could do 51 kilograms multiplied by G and find out what that gave us as a force, all right? And therefore you could then link that back to this idea of the vertical component. So either argument is fine, whichever way you work through it. But 1 mark for calculating the vertical component of the force, and the second mark for linking the size of that force with it being balanced by the weight of the border and working out the corresponding mass of 51 kilograms. As always, they like to throw in things to just show that you have thought about the context. Another, suggest and explain. So 1 mark for each. Okay, now there are various ways you could put this. Again, it probably all boils down to a similar sort of idea. You're linking to the fact that actually you need different size kites for different speeds. Okay, that is the crux of it. So actually, if you were able to say different size kites in different speeds, that would probably get you 1 mark. All right. What you'd need for the second mark is you'd need to identify the fact that actually at certain speeds, so for example at high speeds, you'd get the kites being lifted off the water if they were too small. So there are varying ways you could phrase this, okay, and various ways that you could say it, but it really will boil down to the same thing, identifying the fact that actually different size kites will behave differently in different speeds of wind, and actually, for example, in faster winds, a smaller kite would be lifted off the water. All right, so 1 mark for kind of trying to suggest that different size kites suit different situations. And then the explanation would be that example of a small kite in fast winds getting lifted. And then finally with this one, he's pulled horizontally at a steady speed, okay? Think about what we know about that, steady speed, by the force described in part A. State what this tells you about the forces between the board and the water. Refer to components of forces in your answer. Okay, now if things are at a steady speed, what does that mean about the forces? It means they are balanced, okay? But because we've got 2 marks here, and because it says refer to components, you have to say which forces are balanced, okay? So what have we got pulling in each direction, okay? Horizontally, we know we've got the horizontal component, all right, horizontal component of the force from the kite. So that is what we worked out earlier, all right, that 900 newtons. So we know that that horizontal component of the force from the kite is balanced and therefore equal to the horizontal component of the force from the water on the board. Okay, so the water on the board is acting in the opposite direction. So the first mark for saying that these 2 forces are equal to each other, and the second mark for identifying that they are acting in opposite directions. Now, of course, you could achieve that by saying horizontal component of the force from kite is equal and opposite to the horizontal component of the force from the water on the board. And then we're back to another SUVAT. So good practice once again. We've got a vertical velocity initially of 12 meters per second. This is a stone being thrown upwards. So it's good practice to acknowledge that in this instance, as it's being thrown upwards, acceleration is acting against it. And we are told that it reaches a height of 3 meters, or it certainly does when we're interested by it. Okay, you're being asked to find V. So we need something that's got V, U, A, and S. The only one that you will find is this one here. All right, so in this case, V squared is 12 squared plus 2 times minus 9.8, because it's acting against it, times by 3. All right, and when we do all of that, V squared should come out at 85.2, giving us a V of 9.2 meters per second. Okay, so hopefully that one's quite straightforward. Then with part B, some of you I know over your time have actually had to go at this and you have used kind of quadratic formulae to try and work out values. So if you use S equals ut plus half at squared, you end up with 2 answers. We know that. We know that if you solve a quadratic, you get 2 answers. Explain without calculation how the displacement can be the same at 2 times. Think about it. We are throwing an object up and then that object comes back down again. Okay, so if we reach a certain height of 3 meters, we probably reach it there. And actually, technically speaking, our displacement will also be 3 there. Okay, so the key thing here is that it reaches 3 meters displacement twice. Once on the way up and the once on the way down. Okay, so that's just 1 mark for that bit. Right, so we're on to looking at base jumping, all right, people jumping off structures. So you've got a base jumper from a height of 150 meters, and as usual, accelerating uniformly with 9.8 meters per second squared. Part 1, show that it takes a little over 1 second for the jumper to reach a speed of 12 meters per second. So this isn't quite SUVAT, but you can see what we've got here is we've got a velocity at 12 meters per second, and we've got an acceleration of 9.8. What we are after here is we are after time, and if you remember, time is change in velocity over acceleration is change in velocity over time, and therefore time is our change in velocity, which is 12 meters per second, because they're going from 0 to 12, divided by the acceleration, which is 9.8, which gives us 1.22 seconds, which is just over 1 second. Show that the distance fallen by the base jumper before she reaches this speed is about 7 meters. So now we do go into a bit of SUVAT. All right, what we've got here is we've got a distance that we've been given, a vertical distance of 7 meters. All right, we've got a time and we've got a final velocity. all right? And we know that our initial velocity is 0. So once again, this should really be your default, this equation, when you're looking for distances or times for things in free fall. Usual drill, that will be eliminated because u is 0. And we're doing this when t equals 1.22 seconds. So we're trying to find s, which is our unknown, which is just half times 9.8 times by 1.2 squared. And that gives us a value for s of 7.29 meters, which is approximately 7 meters. So there is that one. Okay, then you're asked to look at the total time taken to reach the ground. So we know now that this fall is split into two parts. There is the part when there is free fall, and then there is the part where there is a steady speed once the parachute has been opened. So we know that T1, if you like, our free fall time, is our 1.22 seconds. So what we now have to do is work out T2, which is the time that was taken to fall at our steady speed, namely once our parachute was open. Okay, so what we first need to say is, well, all right, how far is the distance fallen at this steady speed? And we know that we had a total distance of 150, and we know that actually we have taken 7.3 meters off that, because for 7.3 meters, that's how far we travelled in that 1.22 seconds. So the total distance fallen at this steady speed will be 142.7 meters. And remember, if you've rounded, that's no problem at all. So the distance of 142.7 meters was fallen, and that was fallen whilst travelling at a constant speed of 6 meters per second. Okay, so we apply a very simple bit of GCSE, and we say that the time taken is the distance divided by speed, so 142.7 divided by 6, which gives us a time of 23.78 seconds. But remember, that is just the time it took to fall at the steady speed. So our total time is the sum of those two, which is our 23.78 plus our 1.22, which is very, very nearly 25 seconds. Okay, so just over 25 seconds. And then for part B, you've got a graph described by a model for the jump, and then you're asked to sketch what you would actually see for the base jumper. Okay, so to do this, you have to think about what is actually going on in terms of the velocity of a base jumper as they fall. So initially, we know that they accelerate because initially, when they sort of leap, the weight is the greatest force. There is very minimal air resistance, but air resistance starts to increase the moment they start to fall. So we start with a high speed, okay, with the speed increasing and acceleration, but as time goes on, that acceleration reduces. So we should, rather than having this straight line, we should have a curved line up to this point here, where our gradient is getting less steep. Okay, our model then shows our velocity decreasing almost instantaneously once the parachute's opened. We know that isn't true. We know instead that actually it should be something a little bit more like this. All right, now again, sort of exactly where your curves are don't matter. The key thing is that we should have a sort of convex curve in this first section and a concave curve in our second. We know then it will continue to fall at this steady speed of 6, so that should be absolutely the same as the existing graph. But because the area underneath it, remember, gives us the total distance that has been travelled, the area underneath these two graphs should remain the same, and therefore what that means is that this bit here will be parallel to the original, but it will be a little bit sooner. Okay, so 1 mark for getting that part there sooner, and 1 mark for correctly amending the changes in the acceleration and deceleration. Back to looking at components of forces. So explain why the horizontal component of T is equal to half F. The key thing here is your first mark is for identifying that we have got a system in equilibrium. Okay, so a system in equilibrium, all right, that's one way of saying it. The other way of saying it is that we know that actually our horizontal forces must be balanced, okay? Because that's the same thing. The fact that it is in equilibrium means that our horizontal forces must be balanced, or you could say horizontally no resultant. So any of those three will get you that first mark. Okay. What you then have to do for that second mark is therefore identify that the F here is shared, all right, or in fact it's balanced, balanced by, because that's what's going on. It's shared between, now it's not T, is it? All right, because our T's aren't actually in the horizontal plane. What it is it's the horizontal component. Okay, so F is balanced by the horizontal component of T, and in actual fact it's balanced by two of these. All right, so the two horizontal components of T, and that's why each T has got about half F. All right, because our system is in equilibrium, and therefore that force pulling to the left is balanced by two lots of T components in the horizontal. Then you're being asked to actually find that value in the tension, or rather to show that it's about 90 newtons. So we're told here that F is actually 140. Okay, so we know that F is 140 newtons, and we know that actually the horizontal component of T, okay, must therefore be, T horizontal, must therefore be 70, okay, because we know that it was half, T is half F. So if we've got a horizontal force of 140 to the left, each of our horizontal components of T must be 70 newtons, and we know that that 70 newtons is merely the resolved T cos 36. Okay, so our value for T is then just 70 divided by T of cos 36, which gives us 86.5, which again for our spec, believe it or not, is approximately 90 newtons. Okay, so just to reiterate, if we're not sure where this little bit came from, what we've done is we've said that this force here, T, this is what we're after. To resolve it horizontally, it has gone through the angle. So this thing here will be T cos theta. So that's where I got my values for down there. So another one about resultants. Options here, you can use a scale drawing, you do not have to, you can use a calculation, it's absolutely fine. All right, now what I'll do is I'll draw it out just because it allows you to sort of see what's going on. So we had 15 paces north, okay, so 15 paces north takes us to up there. Then we had 7 paces west, so we had 7 to that point there, and then we had 3 paces south. Okay, so we know from the stuff that we've done previously that our resultant is therefore this one here. Okay, let's break that down. That's made up of 2 parts. Okay, the total vertical displacement, if you like, is simply this side here, because it's simply that 15 minus the 3, and then we've got our side here of 7. Okay, so we know that that one there will be 12 paces and that one there will be 7. Okay, so the easiest thing to do from my point of view is I would use Pythagoras. So we can say that x squared is just 7 squared plus 12 squared. All right, when you do that, that comes out at 193, and therefore x comes out at 13.89 paces. All right, so 13.9 or 14 paces. Absolutely fine. Then you are being asked for the direction. Now, as always with these, just make sure you add some sort of annotation to show what direction you're referring to. So, for example, it would be quite easy to just do this one here. Okay, that would give us an angle. And if you showed clearly that that was the angle you were working out, that would be absolutely fine. So in this case, we would say, well, tan of theta is opposite over adjacent, so we've got 7 over 12, and when we do that, theta comes out at about 30 degrees. So there is option 1, as long as you have annotated to show which angle you're referring to. Strictly speaking, we should give bearings, and remember, bearings are always from the north. So here is our north, and therefore our bearing would actually be 360 minus the 30, so it would be 330 degrees. Okay, so a couple of different answers you could give, but the key thing with these sort of questions is ensure you annotate to show the angle you are giving, and you will probably find that you'd get credit for it. So we're then looking at a rocket with a weight acting downwards and a thrust T being provided upwards by the engines. All right, you have the velocity time graph for this rocket, and a lot of this question relates to coming back to the graph time and time again. To start with, how does the graph show the rocket remains stationary? So we're looking at this whole section here. The key thing here is that you must identify that V is 0 initially. Okay, so it's not sufficient to say it's flat. Okay, you have to identify that the velocity is 0 in order to get the mark. So that's how we know that it takes some time. It is stationary for a little while before it actually takes off. Then we're asked to explain in terms of T and W why it remains stationary for a short while. Okay, so why is it that it does stay stationary? Why doesn't it immediately lift off the ground? Okay, so the key thing here is all about figuring out resultants. Okay, and the fact is that initially we know that actually as soon as those thrusters kick in, the weight is greater than the thrust to begin with. Okay, because it doesn't immediately spring to its maximum. All right, we'll then for a short period get a situation where they are equal. All right, W will equal T, and then eventually we get to this point when T will be greater than W, and that is when it will actually move off the ground. Now, why is it that that happens? Why is it that eventually T is greater than W? That is because actually W reduces, okay, after a while. Think about that. Why does W reduce? Well, the fact is, as the question says, the thrust is provided by ejecting gases. Okay, so your first mark is for identifying the differences in these values of W and T, and your second mark comes from acknowledging that there is a reduction in the weight which allows T to be greater, and that reduction in weight comes because we have a lesser mass on the rocket because it has been ejecting gases. Then we're asked to find the acceleration, all right? So acceleration from the graph, remembering that acceleration, of course, is the gradient of a graph. You're asked to find it at 6 seconds, showing you're working clearly on the graph. Again, something that you lot need to make sure you are doing, and in this space. So the way that this works is we have got a curve here. So what you have to do is you have to do a tangent to the line. So at 6 seconds, you draw a tangent to the line on the graph, okay? Now, I've done this myself previously, and then I'll just do this one to show you. Okay, so you do yourself a tangent, and then from there, you mark up very, very clearly the edges of your triangle. All right, so make sure that you have actually clearly drawn the tangent and that the period of time that you draw that tangent over exceeds 1 second. All right, make it as big as you can. Always the rule of thumb with gradients, make them as large as possible. All right, you then pull your values from there. Now, I've already done this previously, so I'm just going to pop back down to the bottom. Okay, the key thing here was you then do your change in velocity over change in time. And in my case, that was 24 divided by 2.5, which gave an acceleration of 9.6 meters per second squared, which is approximately 10 meters per second squared. And this, again, because you're drawing a tangent, it would allow a range between 9 to 11 meters per second squared. Okay. So next, we're being asked to show that the weight of the rocket is about half the thrust of the engines. Okay, so the first thing to do here is to say, well, what is the weight of the rocket, W? All right, what is that value for W? Well, W is the mass of our rocket, okay, which we know is 6.9 kilograms, multiplied by G, which gives us 67.62 newtons, so about 68 newtons. Remember, we're only showing that it's about, so rounding here doesn't matter too much, okay? We have also, at 6 seconds, worked out the acceleration of our rocket. And because we've got the mass of our rocket, we can therefore work out the resultant force that must be acting on that rocket. So that is the mass times our measured acceleration. So that's 6.9 multiplied by our answer to the above question, which in my case was 9.6. So that comes out at 66.24 newtons. So what we've found now is the weight of the rocket, which is acting downwards, and we've worked out the value of the resultant force, okay? Now, the key thing here is that the resultant force is actually that single force that replaces all other forces acting. So that resultant force is what we've got left when we've taken into consideration the thrust and the weight, okay? Now, if this rocket is moving upwards, as we know it is, it's accelerating, we know that the thrust must be bigger than the weight. So that means that our resultant force is equal to the thrust minus our weight. Okay, so what we can see here is if we then plug these values back in, very, very roughly speaking, we had about 66 there, we had about 60, that should be T, and we had about 68 there. Okay, so when we put that together, we end up over here with a value of 134 for our thrust, which is very, very roughly 2 times the weight of our rocket. So it's only an approximation, but it's this appreciation that the resultant force is the thrust minus the weight of our rocket. And then lastly, you're asked to sketch the graph you'd expect if the rocket had taken off with a slightly greater mass of gas ejected each second. Okay, so what we're saying is the thrust would always have been slightly greater than it was on the curve that we had. So the two things that we have here is it means that simply it's going to take off sooner. All right, so it is actually going to curve up sooner. And the fact is that it's always going to be accelerating faster. So you're always going to have a steeper gradient. So the first thing on your graph should be that it's curving sooner, and it should also be showing that the two lines on them two graphs will actually diverge. All right, so there's one mark and there's the second. And if I go back to the graph, I can show you what I mean. So you would have something that initially, perhaps not quite so early as that, initially is going to curve sooner, and that distance between these two will actually continue to separate and to get bigger and bigger. Now obviously I'm not going to go back on myself, so I've not drawn that awfully well, but what you should be finding is that the acceleration and the gradient of this curve that you've drawn now should always be greater than the original. So maybe something a little bit like that, okay, with the distance between the two getting greater and greater. And back to components. So throwing a wooden ball into a bucket sounds like a fun game, doesn't it? First thing, you're asked to write down expressions for the horizontal and vertical components of U. So remember, horizontally, you are moving it through the angle, and therefore we've got U cos theta. And vertically, you're moving it away from the angle, so you would have U sine theta. There are our two components. You're then asked to show where this equation has come from using the ideas from our SUVAT. Okay, so as I'm sure you realise, we are starting with this thing here, but you're being asked to explain how this thing here ends up with this thing here that we have been given in the question. Okay, now what we have to do here is we have to say, okay, the top of the bucket. So if you go back to our diagram, when it reaches the top of the bucket at this position here, what is its vertical displacement? Well, its vertical displacement is going to be 0. So the first thing to identify is at the top of the bucket, S equals 0. Okay, so this is 3 marks. There's lots of things you have to justify. So that takes us, I'll annotate the equation as we go along. So that takes us to this stage here, half a t squared. Right, what else do we know? We also know that actually U is the vertical component, and we've previously said that that is U sine theta. So when we put that in, we've got this is U sine theta t plus half a t squared. We are nearly there. Okay. What else do we know? Well, we know that in this case, because the ball is being thrown upwards, A is equal to minus G. So when we put that in as well, what we then end up with is 0 equals U sine theta t minus half GT squared. There we have it. So now you're having to use that expression and use that expression to allow us to find the time taken for the ball when thrown with 8 meters per second at an angle of 50. Okay, so if we start by rearranging this, we can say that U sine theta t is equal to half gt squared, okay? So rearrange that. Then we'll find that one of the t's on either side will cancel. So then we've got u sine theta equals half gt. All right, so we've got 2u sine theta equals gt. All right, and when we work through all of that, you end up with t having a value of 1.25 seconds. So 1.25 seconds. And this last one, a little bit more linked with energy, but never mind. It's always useful to think about these sorts of things, and I'm sure you were able to come up with some reasonable suggestions. Another, suggest and explain. So how should you do it differently? Why is that going to make a difference? A couple of things you could have come up with here. Things such as a smaller angle. All right. So if you throw it at a smaller angle, all right, think about what's going to happen. Well, the reality is it may, and it's only a may, it may collide with the sides of the bucket. Okay, so if it did that, what's that going to do? Well, any collisions that it would then have would actually dissipate some of that energy. So it would mean that actually when it did hit the bottom of the bucket, some of the energy would already have been dissipated, so it wouldn't have caused the ball to bounce back out again. So a few options really. I'm not going to go through all of them, but something that would have brought in this idea of dissipating the energy more would work. So a smaller angle. Something else that could have been a suggestion, if you'd actually had a lower value for u. Okay, so if you threw it more slowly, think about that. What's that going to do? Well, when you throw the ball, it gains kinetic energy. But if you have a smaller velocity, then what you're going to do is there will be less energy in the first place. All right, so it'd be another example where you've got less energy to dissipate. Okay, so various combinations of ideas, but we're always looking for something that we can do to reduce the amount of energy that the ball actually has. And smaller angle and smaller initial velocity are the main ones there. Okay, so this is a question that may on the surface look a little bit tricky, but as soon as you read it and get your head into what's going on, hopefully it's fairly straightforward. So you have an object that is moving along a semicircular path from A to C. So it's following this route here. All right, the radius of the path is 3 meters and it's going at a constant speed of 5 meters per second. First things first, show that it takes 2 seconds to get from A to C. Well, look at the distance that it's traveling. It is traveling half a circumference. Okay, so think back, what is the circumference of a circle? Well, it's pi d, isn't it? And therefore the distance that they travel is going to be pi r, which in this case is pi multiplied by 3 meters, which gives us a distance of 9.4 meters. Okay, time taken to then do that, well, you take the total distance that you're traveling and you divide it by the speed with which you're traveling, giving us a time of 1.88 seconds, or approximately 2 seconds. Then you're asked to write down the values of the components of the velocity when at A, B and C. Okay, so let me just remove this to try and help so that I can annotate this as we go through. Okay, so x and y components of the velocity. So in terms of the velocity, what is it doing? Well, at A, it is moving this way. Okay, at B, it is moving this way, and at C, it is moving that way. All right, if you actually physically draw on what the object is doing at those 3 points, that should make it easier. Okay, when we look at that, we can therefore see that there is absolutely no velocity in the x direction at A, and actually neither is there at C. Okay, we can see that the only time there is a velocity in the x direction is at point B, and because it moves with a constant speed, at that point it will be moving with 5 meters per second. If we now transfer across and look at the y component, well, we can see that at A it is moving vertically only, so it will have a component of 5. At B it is moving horizontally, so has no vertical component at all. And then at C it is now moving in the opposite direction but in the vertical plane, and therefore has a value of -5. Having done that, it then asks you to look at the displacement in the x and y components. Okay, so again, thinking about where it is relative to A. Okay, so x component wise, when we get to B, well, B is above this position here. So in the x component, it is 3 meters away. In the y component, it is also 3 meters away. When we get to C, however, in the x component, it is actually 2 lots away and therefore is 6. And in the y component, it has returned back to where it was in the y plane and therefore it is 0. So again, using this idea now of looking at different components of the motion at different times. So we've got the car travelling at position D, where it is travelling in this direction, and then we've got position E when it is travelling in this direction here. Okay, and we've still got our Y and our X. So you're now asked to look at the values of the X and Y components of the acceleration. Okay, so what we need to do firstly is for each component identify how the velocity has changed. So in the X component, at D, we know it is travelling wholly in the horizontal, rather the X, and therefore our U is 12 meters per second, okay, because we're told that it's travelling at 12 meters per second. However, when we get to point E, it is no longer travelling completely in the X component, it is travelling at an angle, and therefore our component in the X direction at E is actually 12 cos 40, okay, which gives us a velocity at that point at 9.19 meters per second. Okay, we can therefore work out our change in velocity, which is our 12 minus our 9.19, which gives us a change in velocity of 2.81. And then our acceleration is that change in velocity. We're told it takes 1.6 seconds to travel, so divided by 1.6 gives us 1.76 meters per second squared. If we then look at the Y component, well, in the Y direction, there is no component of velocity initially. It is travelling in the X. All right, at D, we haven't got any velocity in the Y component direction at all. All right. But when we get to E, then what we're doing is we're saying, well, actually, in the Y component, it is this thing here resolved. So our velocity at point E is this time 12 sine 40. And that comes out at 7.7. Okay, dodgy equal sign. So that means that our change in velocity is 7.7 meters per second, and that change in velocity of 7.7 seconds still takes place in 1.6 seconds, giving us a value of 4.8. So 4.8 meters per second squared. Here we have another velocity time graph, and we're being asked to work out the distance travelled in the first 8 seconds. Okay, so again, with these sorts of things, always remember to show your working. So we have a triangle, and we have a rectangle. Okay, so very, very clearly show what you are doing to work out your areas. So in this case, we've got the fact that it is the area under our graph, which is half our base, which is 5, times our height, which is 10. So that's the area of our triangle, added on to the area of our rectangle, which has got a base of 3 and a height of 10. Okay, so that gives us 25 plus 30, giving us a total distance of 55 meters. Then you're asked to estimate the deceleration of the car at 9 seconds. So again, velocity time graph, acceleration or deceleration is the gradient, but we're on a curve, so you have to do a tangent. So once again, at the point of 9 seconds, you need to draw a tangent onto your graph, and that needs to be clearly visible. Okay, so draw your tangent, and then from that do your working out. Now again, I've done this previously and therefore I'm taking my own values rather than what I'll read off the graph this second. But firstly, make sure you annotate to show your tangent, okay, and then you actually do your working. So I had 11.5 minus 6 divided by 10 minus 8.2. So I had 5.5 as my change in Y. All right, and my change in X was 1.8, which came out at 3 meters per second squared. And anything, all right, between 2 and 4 meters per second squared is allowed, providing you have shown that you have used a tangent to get there. And then C, having been given this velocity time graph, you had to then translate it back. So we've done quite a bit of this, all right, figuring out the other motion graph from one of them. So we've got the velocity time graph, we have to figure out what the displacement time graph looks like. All right, so think it through. What is our object doing? Well, we know that to begin with, its speed is increasing with constant acceleration because it has a constant gradient. So we're looking for something where speed is increasing initially, okay? And from our displacement time graph, an increase in speed is an increase in gradient. So we've only got two of these that are showing an increase in gradient, B and D. So we can immediately disregard A and C. Our second segment then, 5 to 8 seconds, we've got a constant speed. All right, so what does a constant speed look like on a displacement time graph? Well, it is a straight line, okay? Now, we could argue that there's a little bit of a straight line in there, and possibly we could argue that there's a little bit of a straight line in there. So it possibly doesn't help us at this stage. So we have to then look at the last bit. What is happening between 8 and 10 seconds? Well, we've got this line sloping downwards, which shows that we've got a deceleration. Okay, now what does a deceleration look like on a displacement time graph? It is a gradient that is reducing in steepness, and the only one that shows a reduction in steepness of gradient is B. So our answer here should be B. Now the projectiles one here. Okay, quite a common scenario really, this idea of something being dropped, and therefore because it's being dropped from a moving object, it will reach the ground some distance later. Okay, firstly, another show that. It's worth pointing out there are a lot of show that's in these questions. These are because this is our specification, but this is our specification when it was prior to the most recent changes. In recent changes, the style and the nature of the questions is pretty much the same. The only difference I should make you aware of is far fewer of them now are show that's. It would be much more likely that you'd calculate how long it would take. So just be aware of that. I know we've had a lot of show that's as we've gone through this, but there are far fewer nowadays than there used to be, but the style of questioning remains exactly the same. So show that it would take about 3 seconds to land. So usual drill here, as I say, your default really by now should be to leap into this one. If you can't use that one, that's fine, try something else. But in this case, of course, that bit will vanish. So we are being asked that we say it falls from a height of 50 meters. So there is our 50 meters. We've got half, we've got 9.8, we've got t squared. Okay, so t squared comes out at 10.2, which makes t 3.19 seconds, which is approximately the 3 seconds that we are after. Explain why the horizontal distance is given by d equals vt. Okay, so we know that that is simply taking our previous equation of motion and lopping off the end, getting rid of that half at squared. Why are we able to do that? And that's what you should be putting in this question. It's this acknowledgement that we don't have a value for a. So there are several ways you could talk about that. Okay, the first thing that you could say is that there's no acceleration horizontally. Okay, that would get you 1 mark. All right, you could say that the horizontal and the vertical velocities are independent. Okay, so you could say that it's independent. And in fact, sorry, apologies, that wouldn't be horizontal and vertical velocities. You could just say that the horizontal and vertical motion is independent of each other. Okay, so there's another thing you could say. You could say that the horizontal is unaffected by gravity. That's a valid reason. Okay, that leads back to why there's no acceleration. Okay, you could also say simply that the horizontal component of the velocity remains unchanged. Okay, so a few options as what you could say, but it's a 2 marker and therefore you need to say more than one of them in order to get both. So now we're looking for our horizontal range. So we know that our horizontal range is given by S equals ut. We've got a speed of 120 and it's fallen from a height of 50 meters. So we know that we are using the value for t that we just worked out. Now you could use the 3 or you can use the 3.19. I've used 3.19, which brings mine out at 382.8, so very roughly speaking 383. If memory serves, if you've just carried forward the 3, you'll get 384. Either of those is absolutely fine. Another waffle. All right, I know how you like the waffly ones, but please, please, please don't leave these out when doing exam questions, all right? Just have a think, because it is a foolish way to lose marks, because often these are common sense. So even though you may not like them, and even though it's not necessarily very easy to prep for them, these are really important. I'm so tired of getting pieces of work handed in that don't have any answers. So please just have a think. For certain supplies, they must land at a much lower speed, so they use a parachute. Okay. Suggest an item that would need to be dropped by a parachute. So there's your first thing, name the sort of item. It's 4 marks, so 1 mark for the sort of item. Okay, now the key thing here is that you basically go for anything fragile, okay? But be sensible. No people, no food, no animals, okay? No food, people, or animals. All right, so something that is fragile. For example, you could have medicines, all right, you could have electrical equipment, okay, you could have water containers, all right, or liquid containers. Water's probably most likely, or you could even have something like weapons, okay? So 1 mark for identifying the sorts of things that could be dropped or should be dropped from a lower height, so that they're dropped more slowly. The rest of the question is about justifying the consequences, or rather identifying the consequences of if you didn't drop them more slowly, okay? So the things that you now have to focus on is, well, what happens if they're dropped from higher? Well, they could have a longer time in the air, all right? Now think about that. Why is that a problem? Well, actually, you're trying to drop them in a specific place. The longer they're in the air, the greater drift you're going to get. You'd get things like wind, all right? So the wind would affect the motion, okay? You've also got things like wind changes with height. So you know that the wind is a problem potentially, and actually the higher you drop your objects from, the greater a problem that could be causing. All right, so have you got something in there that suggests why being in the air for a long period of time is going to be a problem? And then something else you could make reference to is, well, okay, how do we reduce this idea of drifting or things not landing where they're meant to? Well, actually, we can reduce drift by dropping as close to that 200 meter mark as possible. Okay, so none of this is really physics particularly. It's a bit of common sense, all right? What you need to try and do is, as I say, you get 1 mark for suggesting a reasonable item. Okay, discuss, you can see that it says discuss why using a parachute might prevent it reaching its intended destination. So this is not about damage, okay? So please make sure you've read the question. Nowhere here, as it said, it might break. What we're looking at here is the problems that you get because things don't land where they need to be. All right, and then actually one of those marks is a QWC, all right, but that QWC needs at least 2 factors, all right? So have you said at least 2 of these points here in terms of why things may not reach their destination? Nearly there, folks, well done. So, helicopter. Mass 9,500 kilos, show the upward force the rotors must provide to keep it hovering is about 90 kilonewtons. All right, so very simply we're saying, well, all right, it's its mass multiplied by gravitational field strength, and that gives us 93100 newtons, which is about 90 kilonewtons. So that's the weight of our helicopter, and therefore that's the force the rotors must provide, at least the weight of the helicopter, otherwise it's going to drop out of the sky. Draw a vector diagram showing the vertical and horizontal components of the force when it's tilted at an angle. Okay, so if we add the force first of all, okay, it's tilted at an angle of 20 degrees. So what we've then got is, here is our vector diagram, and we know that this one here would be F cos 20, because that was F, and we know therefore that this one here would be F sine, oops, not sine theta, sine 20, okay? Use the vector diagram to show that the force required to keep the helicopter at constant height must now be nearly 100 kilonewtons. So what we're saying now is actually it's not F that has to balance out the weight, it's F cos 20. So in this case now, F cos 20 has to equal at least the weight of the helicopter. All right, and we know that the weight of the helicopter is 93,000, very roughly. Okay, so therefore, in order to find out what F is simply 93,000 divided by cos of 20. Okay, because mg was that 93000. And when you work that out, F comes out at 99,000 newtons, so nearly 100 kilonewtons. Okay, so now we're being asked to find the acceleration of the helicopter. Now this is a bit of F equals ma, which we haven't really done yet, but it's GCSE, so I think we can cope. All right, so what we're now saying is horizontally, what is the force that we've got? Well, the force that we've got horizontally is F sine 20. All right, and we've just seen from previously that F is actually 99,000. So F sine 20 is 99,000 multiplied by sine 20, which gives us 33,859 newtons. So that is the resultant force on our helicopter horizontally. That is then equal to mass times acceleration. So the acceleration of our helicopter is this resultant force, this 33,859 divided by its mass, and that comes out at 3.56 meters per second squared. Another vector resolution, so looking for a resultant, okay, relative to the ground. So what you might want to do is say, well, all right, let's say that that one is 9, let's say that that one is 24. What we're looking for is this one here. Okay, so in that case, we've got 24 squared plus 9 squared is equal to v squared. Okay, and therefore v squared comes out at 657, giving us a value for v of 25.6 meters per second. Okay, then once again, you are asked for a direction. Okay, so this time you are reference is made to the fact that the helicopter is heading due north and the wind is blowing due east. Okay, now as I said, the normal bearing would be to the north. So if we think about that, well, here is north, okay, and therefore that is what would normally be considered the bearing. Now if we were to do that, let's think this through. Well, actually we can rework this, because that edge there would still be 24 and that one there would be 9. Okay, so in working out that angle, and that is how I would recommend you would do it, but remember, as long as you show the angle, then you will be absolutely fine. Okay, in this case then, when we work out our angle, we've got here that tan of theta is once again opposite, divided by adjacent, so 9 over 24, and when we do that, theta comes out at 20.6 degrees. Okay, now as I say, it doesn't have to be that angle that you show, as long as you annotate very clearly which angle it is that you are looking for. All right, but since you're looking for the resultant, that is probably a good one. Okay, and that's it, folks. So you have now hopefully managed to work through and fix any concerns or queries that you had. All right, and if you haven't quite finished yet, then you've got this to keep referring to as part of your preparation for your Chapter 8 work. Well done.